All right, we're talking about Dalton's law of partial pressures with this lesson. It's one of the simplest concepts. The total pressure is equal to all the parts. All the gases that you put into one container will add up to the total pressure. Very simple concept there. Why do we need to know this? Actually goes back to intermolecular forces. When we talked about intermolecular forces, we talked about the fact that the attraction of the particles makes it harder for those particles to become a gas. We looked at temperature change of evaporation of substances that had hydrogen bonds and didn't, and compared them, and we compared weights of substances. All of those interfere, either the weight or the hydrogen bond interfere with the ability of that particle to become a gas and escape. Gas pressure, vapor pressure, is related to that. If you open a Coke bottle, when you open the bottle, you get that psst sound of freshness, right? You have gas pressure trapped inside there. All right. The fewer intermolecular forces will make it easier for that gas to come out of the liquid. Now, of course, the gas in a pop bottle isn't the pop. It is carbon dioxide. But if you have a water bottle, inside that water bottle, you have a layer of air at the top that has water particles inside of it. So, and if it's hotter, you're going to have more water particles, because the warmer something is, the easier it is for it to evaporate, because the particles move faster and they can escape. They have more energy to escape. So, it's important to understand that when you collect a gas using water, that you're going to have water vapor as part of the gas pressure. Here's a drawing to show you. You've got a beaker and you've turned it upside down, and you filled it with water first and then turned it upside down, and then you have something, as it says, a gas generator, but you have a reaction going on here that is bubbling in there. What's that water? What are those water bubbles going to do? Well, they're going to rise and they're going to displace the water that's in there. So eventually you have gas that has collected, but you collected it over water. Water vapor, because that water can still evaporate, you're going to have some water vapor mixed in with the gas you collected. So we have to take that out when we're calculating pressures for gases. That's considered a dry gas versus a wet gas. Were we to do a lab in class, one of the labs we would have done is we would have used a piece of zinc, and we would have or magnesium, sorry, not zinc, and we would have we mixed it with hydrochloric acid, and we would have collected hydrogen gas and measured the amount that we collected, the pressure, so on and so forth. And we would have actually used that to calculate the ideal gas law constant. So that's when we would have used it in a lab in normal times, not crazy quarantine times. Okay. So if we look at these questions, it says to collect the gas, why is the beaker first filled completely with water? Well, by doing that, you're not going to have any air. It eliminates the air. All right, the water basically keeps air from coming in there. So the only gases you collect are the gas that's being produced and the water vapor. The beaker, what causes the water to go down is water displacement. Thank you, Archimedes. And the gas is pure except for the minute amount of water vapor that is in there. All right. When we do gas problems where we're collecting a gas over water, you're going to need a table. Now, this is the only criticism I have over this worksheet, but this does a nice job of explaining it. But we're going to use kilopascals instead of atmospheres. So far, we've been using atmospheres kind of as a default. So that means our ideal gas constant is going to be different when we use perv-nert. So just a warning. But this table gives us the vapor pressure in a container, depending on the temperature. You'll notice it says why you expect the vapor pressure would increase as the temperature increases. Well, the warmer something is, the easier it is for those water molecules to escape from the water and become gas molecules. It gives them just enough energy to overcome the intermolecular forces. Two containers before, both gases were collected over water, which was probably a higher temperature. Well, the water vapor are the ones that I'm highlighting. Which one has more water vapor in it? B does. So therefore B was the higher temperature. Consider gas A from question 5. The total pressure in this one is 104 kilopascals. If we know that that's 20 degrees Celsius, 104 kilopascals is the total. The water pressure at 20 degrees is 2.3. And we can add that to the pressure of gas A, and then solve for gas A. We get 104 minus 2.3, which would be 101.7 kilopascals. Okay? Consider gas B. Gas B was collected at 35 degrees, so the partial pressure is 5.6. So we have 110 minus 5.6. This is your total. This is the pressure of the water. The pressure of the gas B is going to be 104.4, if I did my math right. Let me check that, because I actually went through and worked this whole problem. Yeah, all right, good, I did the math right. John Dalton was one of the first scientists to quantitatively state mathematical relationship involving gas pressure in any container and the individual gases in the container. Dalton's law of partial pressure says what I've already said. They all add up to be the total pressure. Remember that Dalton gave us our first definitions of what an atom was and what a compound was, and the fact that atoms were made of only the element of that compound, or elements were made of only one kind of atom. Compounds were made of fixed ratios of atoms to make a compound. All right. So we have a container that has a gas pressure of 450. That's your total pressure. And it has 3 different gases. So we know pressure total is going to be equal to pressure 1 plus pressure 2 plus pressure 3. 450 kilopascals is our total. We have hydrogen at 210, oxygen at 125, and nitrogen. So this is going to be pressure of nitrogen. How are you going to solve for that? Well, you simply rearrange it. 450 minus 200 minus 125, and if I've done my math right, that's 115 kilopascals for the pressure of the nitrogen. Question number 9. A tank has neon gas at 350, helium at 275, argon at 410. What's the total pressure in the tank? So we just do 350 plus 275 plus 410, and that adds up to 1,035 kilopascals. Number 10, a certain gas was collected over water. The total pressure of the container was 100 kilopascals. The temperature of the dry gas was 94.4. So remember, we're dealing with total pressure is equal to the pressure of the water plus the pressure of the gas. So 100 is going to be equal to the pressure of the water, 94.4 is the pressure of the gas, minus plus the pressure of the water. Solve for the pressure of the water, we get 5.6 kilopascals. But that's not what the question is asking. It wants to know what temperature was that. So we go back to our temperature chart. 5.6, it was collected at a temperature of 35 degrees Celsius. All right. Number 11, hydrogen gas was collected over water at a pressure of 102.5 and a temperature of 25. After sealing the container, it was heated to 210. What is the final pressure of the dry hydrogen gas? All right, so we know that the pressure, the total pressure, was 102.5, and the water pressure at 25 degrees is 3.2. Plus the pressure of the gas. So we do that math and we come up with 99.3 for the gas. All right, now the next piece tells us that we're going to heat that gas. So we're going to have a starting temperature and an ending temperature. We have a starting pressure. We're going to solve for the ending pressure. So now we're going to use pressure and temperature is Gay-Lussac's law. So we're going to use P1 over V1 equals P2 over V2. Pressure 1 we just calculated to be 99.3 kilopascals, not volume temperature. Mrs. Bush. Temperature 1 is going to be 25 degrees Celsius. 25 plus 273 is 298. Pressure 2 is what we're solving for. Our new temperature is 210 Celsius. We have to add that to 273, which comes out to be 483. And you cross multiply, you end up with 161 kilopascals for pressure 2. All right, number 12, oxygen gas was collected over water at 30. The pressure in the 2.5 liter container was 110. If the container was allowed to expand to 7 liters and the temperature was decreased, what is the final pressure of dry oxygen gas? So first we have to figure out the oxygen pressure. Our total pressure was 110 kilopascals. Our initial temperature was 30. So we're going to take 110 minus 4.2. And we get 105.8 kilopascals of the dry oxygen. Now, we're changing the volume of the container and we're changing the temperature of the container. For this, we're going to have to use the combined gas law. P1V1 over T1 equals P2V2 over T2. So pressure 1 is 105.8 kilopascals. Volume 1 was 2.5 liters. And temperature 1 was 30 degrees, which is 303 Kelvin. Pressure 2 is what we're solving for. Volume 2 is 7.0 liters. And temperature 2 is 273 minus 30, which would be 243. Now, solve for your second pressure. So we cross multiply and see if you come up with 1.7 kilopascals. Okay? Number 13 is going to involve PV equals nRT. First, it tells us the pressure in the container was 105. So we have to find the pressure of the dry gas, 30 degrees. The pressure of water at 30 is 4.2. So we get 100.8 for our pressure. We have a volume. We need to know moles. PV equals nRT. We're going to solve for N. So we divide both sides by the gas constant. Pressure we said was 100.8. The volume is 0.475 liters. Now, for the ideal gas constant, because we're using kilopascals, we have to use 8.31. And our units are liters times kilopascal over mole Kelvin. And our temperature is 303 Kelvin, 30 plus 273. Do the math and we come up with When we do the math, we come up to 0.0190 moles. We want to go to grams, so we multiply by 32 grams in 1 mole. Why do we use 32 with oxygen and not 16? Because oxygen is O2. And we come up with 0.608 grams of oxygen. All right, so that should be enough to get you through the problems in the gas law assignments online, which would be Dalton's law of partial pressures.